Okay, so your token observer is back to tell you things about how you actually measure chemical abundances. And I'm going to go through how we measure chemical abundances in stars, which is my expertise, galaxies, so entire galaxies full of stars, which I hope to soon be my expertise. So here we're talking about spectroscopy of individual stars one at a time. And then when you measure the chemical abundances of the stellar population in galaxies, we have integrated light spectroscopy, where nature integrates the light for us. We can't resolve individual stars one by one, so instead we measure all of their light simultaneously. There's going to be some complications associated with that. You can also measure chemical abundances in the gas phase. This is not at all my expertise, but I thought I'd mention it anyway. And also, we can measure chemical abundances in the gas phase not having to do with star-forming regions. So I'm going to talk about briefly measuring chemical abundances in damped Lyman alpha systems. And at the end, I'm going to talk a little bit about how to measure isotopes, because we were talking about isotopes earlier today. We were talking about deuterium specifically. And yesterday and the day before, there was also some mention of isotopes in the R process and the S process. Okay, so this might be a little bit elementary for you, but I'm going to go through it anyway. So the way that we measure chemical abundances in stars is get a spectrum. The higher the resolution, the better, for a variety of reasons. Each element has its own little signature, or like a barcode, where there are wavelengths that correspond to electronic transitions. So this is literally electrons bouncing back and forth between energy levels. Specifically in stars, we see electrons absorbing energy and jumping up in energy levels. So here's an absorption line due to strontium, and the way that you can measure this is one of two ways. One, you can just measure the entire area under the curve here, which we call an equivalent width. So you can just measure the bulk strength of the absorption line. And another way to do it is with spectral synthesis. So actually measure or actually model the shape of the absorption line. So you can model the shape of the absorption line looks like this. It's called a void profile. The shape of the absorption line is affected not just by processes within the star, so you have convection, which can actually make the lines asymmetric, but you also have to consider what your instrument is doing to the spectrum of the star. There's not really many instruments that can reproduce the intrinsic width or the shapes of these lines as they come out of the star. So with even slightly less than exquisite resolution, you have to figure out how is the spectrograph modifying the shape of the star, and incorporate that into your model of the shape of the line. So something that's easier to do but loses a little bit of information is just measure the area under the curve, measure the equivalent width. You can see other lines have all these shapes as well. Some lines are fatter than others. This isn't just an effect of the smaller wavelength range here. I mean, that's mostly it. But also this sodium line is it's called a resonance line. It's one of the sodium D lines. It's also very, very fat for a variety of reasons, having to do with the conditions in the atmosphere of the star. And that the depth of the line contains information about the abundance. The width of the line also contains information about the abundance, but it also contains information about that particular electronic transition in the star. And there's a variety of processes that can broaden the width of that absorption line. So those are individual absorption lines, but in reality, you have to deal with a big forest of lines, especially as you go to more and more metal-rich stars. So here's what the spectrum of the sun looks like at basically infinite resolution. This is basically the resolution of the spectrum of the sun as it comes out of the sun. So if you had a perfect spectrograph, this is really what it looks like. And you can see there's, as I promised, there are some really broad absorption lines. This is called the magnesium B triplet. Those 1, 2, 3 magnesium B lines. But in between and on top of and on the sides of the magnesium B triplet is all this forest of other lines. And even like in little regions like this, there's lines there too. In regions like that, in between those two tiny lines, there's also lines there too that you just can't even see. There's just lines everywhere. And so to really measure the chemical abundances of these really metal-rich stars, you really have to model the spectrum very, very, very well. This is an entire industry. There's someone at Harvard named Bob Karuk. There's someone at UC Santa Cruz named Ruth Peterson, and these people together spend their entire lives in the mind-numbingly boring task of figuring out what all these lines are. And they do that through a combination of semi-empirical laboratory tests to figure out what the oscillator strengths, the Einstein coefficients of these electronic transitions are, and also just looking at spectra like this, to try to find all of the unidentified lines and identify them. It's a very, very, very laborious task, yes? A flat line would be a black body, that's correct. So what usually when we look at these chemical abundances in spectra like this, what we do is we normalize out the black body profile. So we've just drawn everything at just as a flat line here. So we just normalize to the continuum value. And so the strength of the line is dictated by the ratio of the line absorption to the continuum absorption. So in order to know the abundance of an element corresponding to this line, let's just say that it's iron, you have to know how much iron line absorption there is and also how much continuous absorption there is in that region of the spectrum. It's that ratio that dictates the abundance. So the abundance dictates that ratio. Now, if you go to a more metal-poor star, this particular star is very, very metal-poor. This is one that I discovered in the Sculptor Dwarf galaxy. For a short, very short time, it was the most metal-poor star known outside of the Milky Way. And this particular star has about 1/3000th of the solar metallicity. Yes? Not at all. No, this is a much noisier spectrum than this one. So these bumps and wiggles here are noise. Those are not individual. Here? This one? So this magnesium line is wider because as you go to higher and higher abundance, the intrinsic shape of the line actually gets wider due to collisional broadening in the sun. And so another reason it's broader in the sun is because the sun has a much higher surface gravity than this star. This is a red giant. The sun is a dwarf star. And it's actually the pressure in, so how big the star is indirectly related to the pressure in the atmosphere of the star, but the larger the pressure in the atmosphere, which we observers call surface gravity. So the larger the surface gravity in the atmosphere of the star, the more collisional broadening there is in these lines. There's more collisions between these magnesium atoms. It's from collisional broadening here. So you can tell that because these lines are very, very narrow. See, that line's extremely narrow, but this line's very broad. And it's the same spectrograph, it's the same spectrum. So this is definitely the intrinsic collisional broadening due to for magnesium. Is there a question over there? No, okay, good. And so these metal-poor stars are significantly harder to find, especially when you look outside of the galaxy. The sun is, of course, in our galaxy. This star is outside of our galaxy in the Sculptor Dwarf galaxy. Hey, this is the galaxy that we happen to measure the chemical evolution for 2 days ago. But you can see that a lot of these lines just completely disappear, and all you see is noise left here. And that's just because as the abundance decreases, the strengths of the lines also decrease. So very roughly speaking, the strengths of the line depend on the abundance primarily, and also nearly primarily the temperature of the star. So as the star gets hotter and hotter, the lines get weaker and weaker. So for a hotter star like the sun, it's actually a little bit more difficult to measure the abundances of lines compared to a star at the same metallicity that's cooler, because cooler stars have stronger lines. And so what you can do with this is measure the abundances of thousands and thousands and thousands of stars and build up a metallicity distribution like this. This is a log scale, and this is the metallicity distribution of the stellar halo of the Milky Way. And so this is just one application for why you would go through the incredibly mind-numbing task of measuring all these equivalent widths. You measure, 150 equivalent widths per star. You do it for thousands of stars. You can do the math. It's a lot of measuring of equivalent widths. It's only in the last 5 or 10 years that people have really started to do measuring equivalent widths automatedly. People used to go into IRAF and just fit these absorption line profiles one by one, and it's really, really, really boring. And I couldn't stand to do that, which is why I have a different approach. I model the entire spectrum of the star simultaneously, at least the entire observed part of the spectrum of the star simultaneously. I don't deal with equivalent widths. I think they're boring. And there's another reason that I model the entire spectrum of the star, which is that I don't use very high resolution spectroscopy. And there's a good reason for that. Because as you go to medium resolution spectrographs, there's a very cool thing that happens, which is you can multiplex the spectrograph. So in a high resolution spectrum, what's called an Eshell spectrum, you have 2 dispersing elements. And so one dispersing element spreads the light of the star this way, another one spreads the light of the star this way. So what you get is one order of light that has a very small wavelength range, and then another order of light on the detector that has another small wavelength range, but it's a little bit redder, and then another order it's a little bit redder, another order it's a little bit redder. What that means is that one star takes up the entire detector in these high-resolution spectrographs. But if you have a medium-resolution spectrograph, which has just a single dispersing element, then each spectrum only takes up one row of the detector. And you can stack up stars for however many rows you have on the detector. So if you are willing to sacrifice resolution for sample size, then you can get really, really large samples of stars. And if you can measure abundances from those medium resolution spectra, then very quickly, as for example just one night on a telescope, you can measure hundreds of stars in the same stellar system. And so that was my approach here. This is significantly lower resolution than I showed you for the sun. In fact, it's about a factor of, let's say, about 10 lower resolution than the spectrum I showed you of the sun. And what the black line is the observed spectrum. You can see as we go to fainter and fainter stars, you get noisier, noisier, noisier. And then the red line is the best fit model for that spectrum. So the way you make this model is you have lots and lots and lots of different absorption lines, and you know from the laboratory what the oscillator strengths or the Einstein coefficients for those lines are. And you can just run this line list through a model atmosphere, which tells you the conditions in the atmosphere of the star, and then form a spectrum based on that line list in that model atmosphere. Now what I can do is tweak the abundances of all of those different elements until I can get the best match. And you can see there's lots of different elements represented here. So all the red lines are iron. This is why I told you on Monday that we observers like to talk about iron, even though it violates the instantaneous recycling approximation. Because look how many iron lines there are compared to all of the other stuff. It's just iron everywhere. And then these green lines are other stuff. So it's a mixture of calcium here, titanium here. There's a magnesium line there, and there's a silicon line there. You can see iron just completely dominates the spectrum, especially in this rather red spectral range, which is around H alpha. So the place that I like to do this is in dwarf galaxies, because when we have these medium resolution multiplex spectrographs, it's not like you can get spectra of stars in vastly different parts of the sky. The spectrographs and the telescopes have a limited field of view. So ideally, you want to find a bunch of stars in the same spot, and then you can get spectrum of all those stars simultaneously. There's two great places to do this. One of them is globular clusters, and another one is dwarf galaxies, where you just have a bunch of stars all in the same 15 arc minutes on the sky. And so this is a catalog of a bunch of different dwarf galaxies. This actually continues on to the next page in this paper. This is the updated catalog of dwarf galaxies by Alan McConnachie in 2012. The classic reference, which has thousands and thousands of citations, is Mario Matteo 1998, just in case you're interested in looking up all these dwarf galaxies. There's quite a few of these things. The McConnachie paper has probably about 100 of these dwarf galaxies. And it's been my goal for a long time to measure the abundances for as many of these dwarf galaxies as I can. So one reason you might want to measure the chemical abundances or the metallicities of dwarf galaxies is to learn something about galaxy evolution. And so what I've done here is just plot the average iron abundance of all of the stars in these dwarf galaxies versus the stellar mass of these dwarf galaxies. And you can see it forms a very nice tight sequence. This is called the mass-metallicity relationship for galaxies, specifically for dwarf galaxies. The most massive galaxy on here is shy of 10 to the 9 solar masses. So this is significantly less massive than the Milky Way, almost a factor of 100 less massive than the Milky Way. And then it goes all the way down here to 10 to the 3 solar masses in stars. So this galaxy, and I'm actually calling it galaxy very deliberately, has only 1,000 solar masses of stars. And I'm going to talk a little bit about that in a couple slides. But one of the cool things you can do with these medium resolution spectrographs is build up enough sample of stars that this average, this bracket iron abundance, has pretty small error bars for the most part. And this is telling us something very fundamental about chemical evolution in galaxies, which is that by far, the dominant independent variable dictating the chemical abundance is the stellar mass of the galaxy. It kind of makes sense. If you make more stars, then those stars are going to make more elements. So it's also some interplay with how much of those elements the galaxies hang on to. So galaxies with deeper potential wells can also hang on to more and more of the metals that their stars produce, which is why more massive galaxies tend to be more metal rich. Yes?
Presumably it's classified as a galaxy because it's dark matter dominated.
Actually, we do not know how much dark matter is in Segway 2. I've tried as hard as I can. I only have an upper limit of 2.5 kilometers per second on the velocity dispersion. However, I'm calling it a galaxy for reasons that I will describe in a few slides, which is, yeah, okay. But notice, actually, this is a good time to point out something about Segway 2. You might be very compelled not to call it a galaxy because it lies off the mass-metallicity relationship. This is a log scale. Remember that bracket notation has a log in it. A log base 10 scale. So I'm sorry, on Monday someone pointed out that they spent 2 hours on the workshop trying to figure out whether or not I was talking about log base 10 or natural log. But this is a log base 10, so segue 2 is almost a factor. That's about a factor of 8 off the mass metallicity relationship. So what I think happened here is that segue 2 actually started over here. But most of these galaxies, all the black and the blue points, are satellites of either the Milky Way or Andromeda. And that's a very harsh environment for one of these little tiny galaxies to be in. There's a lot of gravitational tides and a lot of ram pressure that's being exerted on these galaxies. So what I think happened is that segue 2 started off over here, and then all of the stars that were not in its dark matter-dominated cusp got stripped away, and then now it's a factor of 100 less massive than stars. And so segue 2 is a victim of tidal stripping. So that's my best guess about why it's off the mass metallicity relationship. Okay, on Monday we went through a bunch of equations on PowerPoint, which is no easy task. And then we found out what the metallicity distributions are for a variety of simplified chemical evolution models. So we had a closed box where nothing gets in, nothing gets out. We have a pre-enriched model, which I didn't discuss too much. It's the same thing as the closed box, but it starts off with a finite iron abundance in the gas of the stars. The gas of the galaxy starts off with. And finally, we had this best accretion model, which I'm here calling the extra gas or the infall model. And remember, it was a system of 2 equations, which has to be solved transcendentally in a computer, and then you get this metallicity distribution here, which is kind of complicated. And there's 2 free parameters in this model. We have the free parameter of the effective yield, and this m, which remember was not the total mass of the galaxy, but it's called the accretion parameter. And so what we can do with these dwarf galaxies is fit the observed metallicity distributions from medium resolution spectroscopy. Those are the black histograms. And the best fitting analytic models of those metallicity distributions are shown in the smooth curves, the blue, the red, and the green curves. So the point that I want to bring away here is that the smaller dwarf galaxies look a lot more like closed or leaky boxes than the larger dwarf galaxies. As we go to these larger dwarf galaxies, so I've ordered the galaxies here from the largest, second largest, all the way down to the smallest in terms of stellar mass. And for the smallest galaxies, the red or the blue curve fits fairly well. But then as we go up to these most massive galaxies, even Leo 2 and Sculptor to some extent, the green line fits a lot better. And what that green line is indicating is that you have to account for the infall of gas into these galaxies in order to explain the iron abundance metallicity distribution of these galaxies. And the way I like to think about it is that these galaxies actually lived a lot longer. That's how they were able to form so many stars. These galaxies didn't live very long. Their star formation histories were pretty short, less than a gigayear, whereas these star formation histories were about 6 to 8 gigayears. And so there's enough time for these galaxies to accrete gas that powered late-time star formation. But because they accreted gas, we get this peaky metallicity distribution that just doesn't look like a closed box. Okay?
Some of those galaxies have highly steep distributions like those in the second row.
That's right, yeah. What my interpretation of this is you see that it kind of has a sharp cutoff here. There's some measurement uncertainty of about 0.1, 0.2 dex per star. And so if there were a very sharp wall in the metallicity distribution, then the observed distribution would have, sort of a steep wall. Not a totally steep wall, but sort of a steep wall. And the same thing here for Leo 2. So what I think happened here is that these galaxies were actually happily forming stars for a long time, and then all of a sudden they hit the Milky Way, and the ram pressure stripping ripped out all of the gas and instantly truncated their star formation. So these galaxies were well on the way to becoming pretty big, closed box looking things, but then the Milky Way ram pressure stripped them. That's my best guess.
Does the amount of stripping depend at all on the ratio of the mass between the dwarf galaxy and the host galaxy?
The ram pressure stripping depends on the velocity of the galaxy and the density of the hot gas halo of the Milky Way. Okay. So I think the answer is no. I mean, all of these dwarf galaxies are at least a factor of 100 times less massive than the Milky Way.
So if you had a dwarf galaxy over something smaller than the Milky Way, you would see a difference in how much it was stripped?
If you had a dwarf galaxy that was about the size of the Milky Way?
So that was around something.
Oh, smaller than the Milky Way.
Smaller than the Milky Way, yeah.
I think if you saw a difference in tidal stripping there, I think that would be telling you something about the density of the hot gas that's doing tidal stripping around the larger galaxy. Does that make sense? Right, okay, that's good. Okay. So far I've just talked about these metallicity distributions in the context of one element, iron, because it's the easiest one to measure. But as you saw in those spectra, there's elements other than iron represented. Iron is the easiest one to measure because there's so many absorption lines. But there's elements other than iron that are represented there. Apologize for the fidelity of this plot here. But here I'm showing you the magnesium to iron ratio, the calcium to iron ratio, titanium to iron ratio, and then the average of all three of those things to iron ratio. And it's plotted versus the iron abundance. Now you got some idea about what these things meant from our workshop and from the lecture, the first lecture on Monday. But what's happening here is type 1a supernova are turning on. Type 1a supernova do not spit out magnesium or calcium. They do spit out a little bit of titanium. And what happens there is when those type 1a supernova turned on, you get a depression in the magnesium to iron ratio because they're just big iron bombs. I like to call them F bombs because they're FE bombs. They're big iron bombs in the interstellar medium, so they just spew a bunch of iron everywhere, and they depress the magnesium to iron ratio just like this. So what you're seeing here is the dwarf galaxies, which are these squares, compared to the Milky Way halo, which are these colored points. And so what you see is that the dwarf galaxies, the type 1a supernova, turned on at a lower metallicity than in the Milky Way. And the reason is that the Milky Way, or whatever made the Milky Way stellar halo, had a very vigorous star formation history. And it took a very short amount of time for it to get to this metallicity. Now, you can basically think about the time when the type 1a supernova turned on as the same amount of time after the onset of star formation in the dwarf galaxies and in the Milky Way halo. So the Milky Way halo managed to get to here in the same amount of time that the dwarf galaxies only got to there. So that indicates that the chemical evolution in the dwarf galaxies was pretty weak. There weren't a lot of things blowing up, and when they did blow up, those dwarf galaxies were not able to hang on to the metals as well as the progenitors of the Milky Way halo. Any questions about that? Okay, good. All right, so recently there's been some effort to start to try to model like how quantitatively what it means for this magnesium to iron ratio to decline like this. So I've just told you the qualitative approach, but the modeling approach we already did. That was the workshop on Monday. So you can do things like combine the delay time distribution for type 1a supernova with theoretical nucleosynthetic yields for type 1a supernova and type 2 supernova. And what you can do is match the observed abundance distributions for the metallicity distribution, for these alpha to iron ratios, compared to a model, a numerical model for the chemical evolution. And what I've done with this numerical model is tweak a bunch of parameters represented here until I could best reproduce the observed metallicity distribution and the observed decline of the magnesium to iron ratio as a function of metallicity. There's a whole bunch of uncertainties, primarily the type 1a delay time distribution, primarily the uncertainties in the nucleosynthetic yield calculations, especially for titanium. I don't even bother plotting titanium because for some reason the yields for titanium that come out of supernova are a factor of 3 at least, too low compared to observations. I love talking to nucleosynthetic theorists about this because they're convinced that there's something wrong with the observations. They say, oh, you've done something wrong with measuring titanium. But in fact, their titanium yields come out like down here. So I'm convinced they did something wrong with blowing up the supernova. And so in the context of the model I've constructed for Sculptor here, I've deduced that there's some sort of inflow of gas, and it rises, reaches a peak, and declines again. And the reason I'm fairly confident about that is the only way to get a metallicity distribution that looks like this is if the star formation rate rises, reaches a peak, and declines again. Unfortunately, this sort of chemical evolution model can tell you about the relative time, how long it takes for galaxies to start forming stars, but it cannot tell you an absolute time. It cannot tell you when the galaxy started forming stars. Color magnitude diagrams are great for that. Color magnitude diagrams are great for figuring out the absolute age of a galaxy. They're pretty bad at figuring out the relative age. So this is a very complementary approach to photometry, where with spectroscopy we can figure out relative ages for galaxies or durations for star formations. In the color magnitude diagram, we can figure out absolute ages. So from the color magnitude diagram, I can tell you that t equals 0 is around 11 or 12 billion years. So pretty soon after things around the Milky Way started forming.
Why are the theorists so convinced about titanium?
I don't know.
You know, I could see with silicon and calcium and magnesium because these are things made in hydrostatic evolution of massive stars. And so that will get blown off when the whole envelope gets blown off.
Yeah.
But titanium, part of that is coming from down in the collapsing core, so it's sensitive to issues like
Fallback.
fallback.
Yeah, that's right. Maybe they're telling me in jest. Maybe I misinterpreted there. They're joking about how confident they are in titanium. It's possible I'm misrepresenting their confidence. Okay. Okay, so, right, I was talking about the metallicity distribution. In order to reproduce this shape, the star formation rate has to rise, reach a peak, and decline again. And so as long as the star formation rate is tracking the gas mass, then I can also say something about the inflow rate of gas onto the galaxy. The gas mass also has to rise, reach a peak, and then decline again. An interesting thing to note here is that this red line is the stellar mass as a function of time, and this blue line is the gas mass as a function of time. At the peak gas mass, look at this ratio between the gas mass and the stellar mass. It's like a factor of 10. These galaxies are absolutely horrendous at hanging on to their gas, and they're absolutely horrendous at hanging on to the metals coming out of their supernova. If they weren't horrendous at it, they'd be much more metal rich. Remember, in the closed box model, the average metallicity approaches the yield of the supernova. Here, we have an average metallicity that's significantly less, like a factor of 20 less than the yield of those supernovae. So we know that the galaxies are at least losing tons and tons of metals, and this probably means they're also losing tons and tons of gas as well. There's a whole bunch of uncertainties that, some of which I've talked about, but would I bet my life that this looks, pretty close to the star formation history of Sculptor? No. There's probably all kinds of bumps and wiggles in the star formation history, burst and other bursts there, that I just cannot accurately reproduce with such a simple model and with the error bars associated with those chemical abundance measurements. Okay, I promised to tell you why I thought Segway 2 was a galaxy and not a globular cluster, for example. Remember, it lies off the mass-metallicity relation, which would argue against it being a galaxy. It only has 1,000 solar masses of stars, which is kind of counterintuitive when we think about what a galaxy is. But I'm going to argue that it is a galaxy based on its chemical abundance distribution. We know that it has a large spread in the metallicity of stars, because I've measured the metallicity of about a dozen of the stars in Segway 2. There's not that many stars to choose from. I can only measure bright stars, which means I only measure red giants in these dwarf galaxies. I cannot measure main sequence stars in these dwarf galaxies because they're at 23rd, 24th magnitude. You only measure stars with 20th magnitude or brighter. So I've measured all of these black points in Segway 2. And the first thing that you notice is that there's a significant spread in the iron abundance in Segway 2. There's a difference of a factor of 30 between this metallicity and this metallicity. That's very different from a globular cluster. A globular cluster is monometallic, has all of the same abundance of heavy elements. And another thing is that you see a decline in these alpha to iron ratios. You sort of see a decline in calcium. That's not that convincing. You see a more convincing decline in silicon. I've only measured 3 stars in magnesium. Titanium's pretty convincing. When I average them all together, you can see that there's a decline in the alpha to iron ratio in Segway 2. And in fact, it looks just like a more massive dwarf galaxy, which is the Ursa Minor dwarf galaxy. Those are the pink points. And so my argument for Segway 2 being a galaxy is twofold. One, it managed to self-enrich. It was able to hang on to supernova ejecta and self-enrich and have multiple generations of stars that were each successively more metal-rich than the previous one. And it lived long enough to have type 1a supernova influence its detailed chemical abundance distribution. So not only did it self-enrich, but it lived for longer than the delay time of a type 1a supernova. And in fact, it lived for longer than the delay time of several type 1a supernova. So that's my argument of why it's a galaxy, because it was able to self-enrich. And the only way that it could possibly be able to do this is if it, at least at one time, had a significant amount of dark matter. That may not be true today because it's been tidally stripped a lot, I think. But at one time, it was a lot more massive enough to hang on to these supernova ejecta. Today, its stellar mass cannot possibly explain how it could hang on to supernova ejecta. So my guess is that in the past, it had a significantly larger dark matter halo than it does today. Any questions about Segway 2?
So what fraction of the dark matter has been lost? Can you estimate that?
Yeah, so it can sort of estimate that based on models of tidal stripping. So there's a model that I like from Jorge Peñarrubia in 2008. And in order to even begin to affect the stellar distribution, so the dark matter is much more extended than the stellar distribution. And even to even begin affecting the stellar distribution, you have to remove 90% of the dark matter from the galaxy, because the stars are very deeply embedded in that dark matter subhalo. And because
What's relevant for indirect dark matter search, and most relevant probably, at least for WIMP annihilation, is the internal, the core.
the central dark matter density, yeah, because it goes as density squared.
That model you're mentioning really doesn't get touched.
That's correct. That's correct. Now, the stars have been tidally stripped by a factor of 30 to 100. So it might be that Segue 2 is not going to survive its next pericentric passage, because this might be the last gasp of this galaxy, which is why I've only found one that lies off the mass metallicity distribution. Okay. Now I'm going to move on to stuff that I'm less familiar with. So previously I was talking about measuring chemical abundances for individual stars from spectroscopy. Now I'm going to be talking about measuring chemical abundances in other systems. So here I'm going to be measuring the chemical abundances in the stellar populations of entire galaxies, not individual stars. And here nature does something for us, which is to blend all of the light of the stars together. In some ways that's kind, because then we don't have to measure individual stars, 1 million or 1 billion individual stars. In some ways it's kind of devious, because then we have an entire initial mass function, or a present-day mass function of stars, all blended together. So we have to know what the age of the population is. We have to know at least something about the chemical distribution of the population, because we have to know where to look in the color magnitude diagram to see where this spectrum is coming from. So the light of this integrated light spectrum is dominated by the brightest stars. And the brightest stars are the red giants. There's not very many red giants, but they're very bright. And the main sequence turnoff. The main sequence turnoff isn't very bright, but there's tons and tons of stars in the main sequence turnoff. And so that's why this integrated light spectrum is dominated by those two places in the color magnitude diagram. And it's not that bad of an approximation just to sample the light of a few red giants in your model of the spectrum, and then the light of a few main sequence turnoff stars. And so what you can do with integrated light spectroscopy, there's two approaches. One, fully modeling the spectrum, which I'll get to in a bit, but another is measuring these equivalent widths, or something called Lick indices, also called spectrophotometric indices. So you can basically figure out how much absorption is in these bands and how much absorption is in the side bands away from them. Take the difference between them, and then you get how much absorption is in that particular metal-sensitive feature. And then there's models of how much absorption there is based on which chemical abundance you're looking at. So for example, if you plot the equivalent width of this iron feature versus the equivalent width of this magnesium B feature, you can draw these models through that space that tell you the alpha to iron ratio of that entire population of stars. Now, if you're smart, you can do this with galaxies at significant cosmological redshift. And so measuring the stellar metallicities of galaxies beyond redshift of 0 is a very, very new thing. So this is work by Anna Galazzi et al. I wanted to do this, and she scooped me, and she did an amazing job of scooping me, of doing this, but that's fine. She's my friend. She can do that if she wants to. And so what she's done here now is measure the metallicity of galaxies in integrated light, so the metallicity of the entire galaxy, the average metallicity, the light-weighted metallicity of the entire galaxy, and plot that versus stellar mass. What you see is that at a high stellar mass, and we also see this in the local universe, the mass-metallicity relationship turns over. It starts to get flatter and flatter and flatter. There's some sort of saturation point for these stellar metallicities. So remember, in dwarf galaxies, there's a very steep mass-metallicity relationship. But in these high-mass galaxies, it starts to turn over and get flatter and flatter and flatter. And that's true not just at redshift 0, but it's also true at this redshift 0.7 galaxy population that Anna is looking at here. Now, an even better thing to do than measuring indices, Lick indices or spectrophotometric indices, is completely modeling the entire spectrum. And so this is something that Charlie Conroy is really championing. He's a professor at UC Santa Cruz, moving to Harvard. And what he does is, with very sophisticated line lists and very sophisticated model atmospheres and very sophisticated models of the light distribution of the stars and galaxies, is model the complete emergent spectrum from a galaxy. And you have to do this at very, very low resolution, not because your spectrograph can't handle the resolution, but because for large galaxies, they have a velocity dispersion. In large galaxies, they make the resolution of the spectrum lower for you, and you don't have a choice about it, because the stars are moving around like this. And so what that means is you have all these Doppler shifts blended together. And so an absorption line that looks very narrow in one star, when you have a whole population of stars that has a velocity dispersion, is going to be very broad and much shallower when you have to deal with that velocity dispersion. And so that's one disadvantage to using integrated light spectroscopy in large galaxies, is you have this velocity dispersion. It's very frustrating because large galaxies are bright. So you can get really, really high signal-to-noise spectrum for these galaxies. But they also have large velocity dispersions, which means that you have to deal with the lower resolution that accompany those bright galaxies. And so one thing Charlie has done, and this is absolutely crazy, and it completely stunned the chemical abundance measurement community when he started proposing that he can do this. He proposed that he can measure individual elements, and not just individual elements, but a lot of individual elements from the integrated light spectroscopy of galaxies when you abandon Lick indices, when you abandon spectrophotometric indices, and instead fit the entire spectrum simultaneously. So he said, I can measure carbon, nitrogen, oxygen, sodium, magnesium, silicon, calcium, titanium, and iron all simultaneously in this one spectrum of the integrated light of a galaxy. This is crazy because just let's take silicon, for example. Silicon does not have very many strong lines. And so what he has to measure is flux decrements changes when he changes the silicon abundance by, say, half a dex. This is the percent change that he gets in the spectrum as a function of wavelength. So he has to be sensitive. He has to have spectra that are good enough to a few percent, just a couple of a percent change in order to be able to claim that he's measuring this. Not only do the spectra have to be good enough, but the models of the spectrum also have to be good enough to be able to measure this. So the jury's still out whether Charlie is measuring what he says he's measuring, but I have no really great scientifically grounded reason to doubt him. I think what he's doing is really, really awesome. Here's another reason to convince you that he actually knows what he's talking about. This is a plot of the element to iron ratio as a function of the atomic number of the element. So he's labeled them for you conveniently, so you don't have to remember which atomic number goes with what. Carbon, nitrogen, oxygen, magnesium, silicon, calcium, and then the iron peak. What he's color-coded here is the high sigma galaxies, so the very massive galaxies that have a large velocity dispersion, and then the low sigma galaxies that have a low velocity dispersion. Now, just in case you say, well, maybe this change in these abundances isn't affected with velocity dispersion, what he's done is he's convolved all of the galaxies with a Gaussian so that they all have the same apparent velocity dispersion. So he's degraded the resolution of these galaxies to match the resolution of those galaxies, and then measured their chemical abundances. And he still recovered this trend where massive galaxies have higher alpha to iron ratios than lower mass galaxies. And this looks just like the difference between the Milky Way and those dwarf galaxies. Remember, those dwarf galaxies had lower alpha to iron ratios, lower magnesium to iron ratios than the Milky Way. And that seems to persist all the way up to galaxies almost on the scale of galaxy clusters. So these are massive, massive elliptical galaxies. So it's pretty incredible what you can do if you have high enough signal to noise and good enough models of the stellar spectra. Okay, let's move away from stars now and talk about measuring chemical abundances in gas. This is not at all my expertise, but I thought it would be unfair of me not to mention all of the different ways to measure chemical abundances in the universe. So when you look at a spectrum of a star-forming galaxy, especially if you have one of these H-alpha filters, you can see all this red stuff, and all that is star-forming region. Those are H2 regions that are forming stars. And it's in those regions that you can measure the gas phase abundances of galaxies. And so what you do now in the gas phase is not deal with absorption lines, but with emission lines. When you take a spectrum of one of these H2 regions, you see lots of these emission lines poking up like this. These are not sky lines. These are not cosmic rays. These are actually emission lines corresponding to H-alpha and a bunch of different metals, nitrogen, silicon, oxygen. What you can do is measure the widths of those lines, or the equivalent widths of those lines, how strong they are. And then this is a classic paper on how to turn those equivalent widths into chemical abundances. And so you can plot the nitrogen 2 to oxygen 2 ratio against solar metallicity, and then this is now an empirical relationship between this ratio, this equivalent width ratio, and the metallicities of stars. And so this is done for galaxies which we know the metallicities for very well, but now we can go to different galaxies for which we don't know the metallicities, measure these equivalent widths, and then look up what the metallicity is based on this empirical relationship. The most famous application of this particular technique is this paper by Tremonti et al. 2004 with over 1,300 citations, where she and her collaborators looked at the gas phase metallicities of Sloan galaxies, exactly using that technique of looking at the nitrogen 2 and oxygen 2 lines. and then plotting their metallicities versus stellar mass. And then remember that mass-metallicity relationship for stars, it also persists in the gas. That shouldn't be too surprising. So the gas phase metallicities of galaxies also obey a very nice tight correlation with their stellar mass as well. And again, this is probably a sequence of metal loss. Galaxies that aren't very big cannot hang on to the metals that their supernova produce, and therefore they end up more metal poor. Another application of measuring the gas phase metallicities of galaxies is to look for abundance gradients. And so what happens here is we're measuring the gas phase metallicities of H2 regions as a function of radius in large galaxies. So I can't remember which galaxy this is. It's probably like M81 or something. But what happens is you have this depression of the oxygen abundance of these H2 regions as you go farther out in the disk. So what this indicates is that the central parts of galaxies are better at hanging on to their metals than the outer parts of galaxies. Yes? There's two processes. So during the lifetime of star formation, the dominant process is probably supernova feedback. So you have a lot of energy being injected from these supernovae that push the metals out. And in fact, a lot of these metals, I suspect, are just directly pushed out. They never get incorporated into the interstellar medium. When the supernova blows up, a lot of its metals get directly injected into outer space. That's correct. And it has a very shallow potential well, so it just can't hang on to this stuff. And it also entrains a lot of the ISM with it when these supernovae blow up. But at the very last phase of the galaxy's life, if it's a satellite galaxy of a larger galaxy, is the ram pressure stripping that serves to completely truncate star formation. Oh, so you're asking, can we see the metal mixing from 1987A, or can we see the metals being ejected from the LMC? That's a good question. I actually don't know. That's a very good question. I don't know how you would measure what the metals are doing out of 1987A. I don't know the answer. It's an excellent question. So one thing that you'd have to, so you could like look at the ejective velocity of the metals coming out of the thing, but then you have to also know how much stuff it's going to run into before it can leave the LMC. So even if it achieved escape velocity now, it also would have to run into a bunch of stuff before it could actually get out of the LMC. So there's the theorists who think about metal loss from galaxies have a phrase for this. It's called the metal loading factor, or the mass loading factor. How much of the mass actually gets, when a supernova blows up, how much mass does it actually bring out of the galaxy with it? Yeah, that's an excellent point. Yeah, it depends. I think it's a supernova on the outskirts of the galaxy. Yeah, that's right. Yeah, not only that, but if the supernova is deeply embedded in the galaxy, in the center of the galaxy, then it's going to entrain a lot more stuff than it's in the outskirts. And so that's one of the primary differences between type 2 and type 1a supernova. Type 2 supernova are deeply embedded in the ISM of star-forming regions. So when they blow up, they're going to affect that ISM and affect the star formation of the galaxy, whereas a type 1a supernova doesn't necessarily have to be around any gas at all. And so it may not affect how much mass loading there is in the galaxy. Okay, so you can measure the abundances not just in the optical, but you also can measure them in the X-rays. I know absolutely nothing about this. I think there's at least someone in here I was talking to at lunch on Monday who does know something about this, so you can ask him. I just thought I'd point out that you can measure emission lines not just in the optical, but there are also other regions of the spectrum. Okay, now let me very briefly, I'm almost done here, so let me briefly talk about measuring the chemical abundances in damped Lyman alpha systems. So the way you do this is that these systems don't emit light, at least not in this range of the spectrum, by themselves. So what you have to do is you have to have a background light source. And the background light source shines through the gas of these damped Lyman alpha systems. Some of that light is absorbed depending on which elements and how much of those elements are in the gas. So usually the background light source is quasar, but there are all other people who are using galaxies as background light sources. So galaxies probing galaxies. One of these people is Kate Rubin. And one of the people who measures quasar background light sources is Jason Prochaska at UC Santa Cruz. So here you see a silicon 2 line. It's very deeply absorbed. Iron 2 line, silicon 2, aluminum 2. You can measure all of this stuff in these DLAs. It's very exquisite data that you can get out of these DLAs. And what's interesting is it doesn't matter how big the DLA is, it doesn't matter how bright it is, because it's not bright at all. The signal that you can get out of this depends on how bright the quasar is behind the galaxy. And it depends on the impact parameter of the quasar behind the galaxy. If the quasar is right in the center of the DLA, that's great. If it's way off here, then you're only getting just the outskirts of that damped Lyman alpha system. And so what the people who measure this stuff do is fit these absorption line profiles. So for example, that is the Lyman alpha. It's called damped because it's so completely saturated. The line is so completely saturated that the absorption actually touches 0. It's completely opaque at the wavelength of Lyman alpha. And then once you know where the wavelength of Lyman alpha is, you know what the redshift of this DLA is. And then you can look where you happen to know other absorption lines to exist and measure their strengths as well. And you can turn that into chemical abundances. So you can get very detailed chemical abundances of these damped Lyman alpha systems. This paper is from 18 years ago. You can do all this detailed stuff 18 years ago. So you can measure silicon, sulfur, zinc, manganese, chromium, nickel. You can measure all this great stuff as a function of metallicity. And you can do chemical evolution models in the universe, not just in galaxies. Here's one really cool result that came out 2 years ago. This is a damped Lyman. The black boxes here are basically the error bars for the chemical abundances of a damped Lyman alpha system at a pretty significant redshift. I think it's like a redshift 3 or 4 or something like that. And what these stars are theoretical predictions of nucleosynthetic yields for a single supernova. And on the left, you're looking at the theoretical nucleosynthetic predictions of a single supernova of a POP3 star. In other words, 0 metallicity. So one of the first stars in the universe that has absolutely 0 iron abundance associated with it, at least before it blows up. Oh, okay, not a question. And it looks really, really, really close to what this particular damped Lyman alpha system looks like. And so one thing that you could interpret from this plot is that this damped Lyman alpha system was enriched by a single population 3 supernova. So it was enriched by the first supernova ever to blow up in the universe. Nothing else ever enriched it. So that's pretty cool, until I show you the right plot. Sorry, I got your hopes up. But these are separate nucleosynthetic yields, the orange for a population 3 0 metallicity supernova, and the blue for a 1/20th solar metallicity supernova. So you can see if you go to a different person and ask what is the nucleosynthetic yields of a population 3 star, you get a different answer. So these are the yields from Hager and Woosley, and these are the yields from Cieffi and Lamongi. So it depends on who you ask whether or not the population 3 supernova yields match the chemical abundance of this damped Lyman alpha system. And really, the only element that's that far off in the Cieffi and Lamongi yields is nitrogen. So this is why I say that one of the dominant uncertainties in the chemical evolution models that I do for dwarf galaxies is the predictions of nucleosynthetic yields. So I've done this experiment where I use the Woosley and Weaver yields, and then I go to the Demoto et al. Yields, and I get pretty different answers, even though they're modeling the same kinds of supernova. Okay, very briefly, I will now talk about how to measure isotopes in stars. So far, I've only talked about measuring chemical abundances, but I have this dream of measuring isotopes for a bunch of different isotopes in the same star. So people have measured stellar isotopes before, but not in a particularly holistic fashion. So they usually look at just one element and measure the isotopic distribution in a star of that one element. What I think would be really interesting is measuring the isotopic distribution for a bunch of different elements in the same star. And then we can do these chemical evolution models, not just for elemental abundance patterns, but for isotopes. And if you remember that yield table that I showed you from Woosley and Weaver 1995 on Monday, they didn't list elements, they listed the isotopes. They can say, you know, this isotope of magnesium, magnesium-24 comes from this, magnesium-25 comes from this, magnesium-26 comes from this. And so if we can measure isotopes, that's a far more precise look at the chemical evolution, the isotopic evolution of a galaxy. Unfortunately, it's very, very, very difficult to measure isotopes, at least for elements beyond helium. So in a star, this is how it's done. the absorption line has some finite width to it. Remember, that finite width persists no matter whether or not you're using a high-resolution spectrograph or a low-resolution spectrograph, because the emergent spectrum from the star has some finite width due to the conditions in the atmosphere of that star. Unfortunately, the isotopic splitting is very, very, very narrow in wavelength space. So this is an absorption line due to europium. So what we see here is all of the absorption lines, all of the many different absorption lines due to europium-151, and the dashed lines due to europium-153. Let me see if I got that right. I believe I got that right. I think the solid lines are europium-151 and the dashed lines are europium-153. And so the reason that there are these different lines based on different isotopes is because the reduced mass of a nucleus is different depending on the number of neutrons you have. And there's also one other effect. There's a mass effect and something else that I forgot. So the key to measuring the isotopic distribution of this europium line is not the strength of the line, but the shape of the line. And you can see if I completely remove europium-151, so the solid line is europium-153. If I completely remove europium-151 from the star, then I get this shape. And if I completely remove europium-153 from the star, then I get this shape. So the key is to measuring the shape of this europium line to figure out what the ratio of 151 to 153 is. Unfortunately, europium is the easiest element to do this for. And so here I'm just showing the same thing, but my own plot of this star with varying europium isotopic ratios. So I'm varying the europium from 0 to 1. Europium is the easiest element to measure, but it's also not very interesting. It's the least interesting element to measure because you always get the same answer, 0.5. And that's simply because europium is an R process element. It's almost exclusively an R process element, and the R process always makes the same europium-151 to 153 ratio. A much more interesting element to measure is barium, because it's made about half in the S process, about half in the R process, depending on which stars you're looking at. That's great. It's scientifically great to measure barium. Practically speaking, it's almost impossible to measure the isotopic ratio of barium. So barium has about 5 different dominant isotopes. And the key thing, the simplified way to look at those isotopes is what fraction of the isotopes are odd, and what fraction of the isotopes are even. And that's because the F-odd ratio for a pure S process is about 11%, and the F-odd fraction for a pure R process is 46%. And so as AGB stars turn on in the galaxy, we can expect this F-odd to drop from 46% to 11%. Now this is the difference between 46% and 11%, the difference between the red line and the blue line. So it's a very, very tiny difference, and the difference is just a few percent. But hey, if Charlie Conroy can measure a few percent in the integrated light spectra of galaxies, surely I can measure a few percent in a high-resolution spectrum of a single star. And so this is what I want to do for a bunch of different stars in the Milky Way using exquisitely high-resolution spectroscopy. Now finally, I'll just mention the easiest isotope to measure, which is hydrogen versus deuterium. So this is, again, a damped Lyman alpha system. And you can tell it's damped because this is what the spectrum around the Lyman alpha line looks like. Completely opaque. But if you go to all of the other Lyman transitions, so here's your Lyman 10, Lyman beta, gamma, all the way up to Lyman 18. Can you see these green dashes there? I'm sorry if you can't see them, but I'll just point them out. There's a couple of green dashes, a couple of green dashes, a couple of green dashes. That's deuterium. And these couple of red dashes, that's hydrogen 1. And so the way you measure the difference between hydrogen and deuterium in a damped Lyman alpha system is you just measure the strength of this line versus the strength of this line. It's pretty easy. So hydrogen has a very large isotopic splitting, thankfully, and you can actually do this. OK, so I'll end there. Thanks very much.
I would just say that what's not easy in that measurement is deciding whether or not that other little nubbin there is the isotope shifted line or another fly.
That's an excellent point. That's an excellent point. Yes. So if you have something bright in X-rays, it's great, but most stars are not bright in X-rays. But like supernova remnants, yeah. Yes.
How do you predict titanium yields compared to like Cat A? They measured it very well.
I'm pretty sure nobody gets titanium right. I'm not totally sure about that, but I'm pretty sure nobody gets titanium right, no matter where you look.
I think that compare those yields. You put those yields in your box.
Oh, you mean get like empirical yields
Yeah.
from Class A? Well, I've never tried that. It's a good point. I'm not sure what can be measured in Class A. So there's certain elements that are easy to measure in these supernova and some elements that are possible to measure. So if I have a significant overlap between the ones that I can measure in stars and the ones that can be measured in Class A, I could try that. Yeah. Okay.
So, where in this, you've given this beautiful picture of the evolution of the elements, especially in dwarf galaxies, for example. So, where do the ultramental core halo stars fit into this picture? Where are they coming from, and what, if anything, do they tell you about? You know, they're kind of a key target for our process studies because they show so much our process material, right?
That's right.
And they have a solar system abundance distribution, at least for the heavier guys.
Right.
So what are they telling us about, how do I fit those things into this picture, if at all?
So the classic picture is that those really ultrametal poor halo stars came from the disruption of dwarf galaxies. I mean, this is Anna Frable's. She's been saying that for a long time, and she has the data to prove it. Not prove it, but the data to support it. Go ahead.
Go ahead.
I mean, if you look at the most metal poor stars in the halo, they kind of have the same abundance pattern as the most metal poor stars in the dwarf galaxies.
Well, is there some way to tie that, though, to the history of stripping, of ram pressure stripping,
I see.
dark matter stripping, and stripping of stars as well? I mean, how do I know that those weren't, very early and very small things that, went into the galaxy very early on, and they're gone now?
Right.
Or do I know, or can I tie them? Do I know enough about their space motions, for example, that they can be tied to, things
existing.
I can point to and say that's a dwarf galaxy?
Right. Unfortunately, I think the answer is probably closer to the former, and it's for the following reason. If you look at the abundances of dwarf galaxies, which are these squares, it looks nothing like the abundance of the Milky Way. And so if dwarf galaxies made up the Milky Way halo, then it's dwarf galaxies that do not look like the surviving dwarf galaxies, at least in this metallicity range. And it's probably true also in lower metallicity ranges, because presumably whatever made up the halo had really metal poor stars. In fact, we know that the halo has really metal poor stars. So unfortunately, I think the answer is going to be the thin and thick disk are the green and the red points. The blue stars are the halo.
So you're saying
They do not agree. They do not agree. So there's this downward trend of the magnesium to iron ratio at this metallicity range for the dwarf galaxies. You don't see any blue dots down here. That's correct. So unfortunately, I think the dominant thing that's making the halo does not look like surviving dwarf galaxies. But that doesn't mean that dwarf galaxies didn't make the halo. It could be a different type of dwarf galaxy, specifically slightly more massive type of dwarf galaxy that was able to enrich to this before the supernova type 1As turned on.
And finally, I have another question, this meta question that I asked you at the beginning of your lectures, which is that I'd like to believe that, what can we do with a 30-meter telescope? What I want is actual distribution of dark matter in these things.
Okay.
Right? I want the nature of the dark matter.
Yep.
So I want to know whether there's a core or a cusp.
Yep.
In these dwarf galaxies.
Yep.
Can you?
I can make an argument for the TMT right now. All right, I'm going to sell you on the TMT. I don't need to because you're at the UC, but if you were thinking of buying into it and that's what you cared about, then I would argue that it's best to look in the most dark matter dominated systems to figure out the presence of dark matter. Otherwise, you have the stellar mass distribution screwing up your velocity dispersion. However, the most dark matter dominated systems are the ones with the fewest stars. So for example, Segway 1, Segway 2, they only have a handful of red giants in them. It's hard to get a robust velocity dispersion from a handful of red giants. So you have to go down to the main sequence, which means you have to go down to fainter stars. Keck cannot do that. The TMT can. Is that convincing?
Yeah.
Good.
The basic argument is that we'll be able to get a better distribution of dark matter from looking at velocity dispersion in the fainter stars.
That's right. You'll be able to get a better sampled velocity distribution. And you'll be able to do it as a function of radius. We can't do that now because we don't have large enough sample sizes.
Okay, now I'm happy.
Okay.
Thank you very much for these lectures.
All